Morning.
Morning.
How are you? Good. So we talked last time about observers. We talked before that about controllers. And we assumed that our system is always observable, controllable. So we can design any kind of controller or any kind of observer that we would desire for our system. But this time I want to talk a little bit, and this hopefully will be a relatively short introduction into systems which are not controllable, not observable, or both. So then what? What should we do with that type of systems? And for that type of systems, we have special canonical forms, which are non-minimal canonical forms. If you remember, minimal systems, where you do not have any cancellations between zeros and poles, they also always controllable and observable. Okay, so if you do not have any cancellation, everything is great. You can design whatever you want to put poles wherever you want, and so on. But if systems have cancellation, some of those poles which are canceled could be non-observable, not controllable, or both. Okay, they must be one of the above. Okay, they cannot be both controllable and observable because they were canceled. So you cannot really move them anywhere in space because cancel them in open loop. So they, in a sense, do not exist in the system mathematically. Okay. So here's motivation for developing all of these canonical forms, and we will do it relatively slowly just for you to understand what it all means, because in that case, it's also important to visualize the type of systems which are not controllable or not observable. So in our case, we want to deal with non-minimal systems, and we want possibility of controller and observer design to see if we still can control the system somehow, or if we can estimate from input and output the state of the system to put controller in, if you do not have to measure all of the states. And for that, we will learn canonical non-controllable form, canonical non-observable form, and we will also talk about stabilizability and detectability of the system, which are expansions of the terms controllability and observability for that type of systems. Okay, any questions so far? So this is the topic for today. Okay, so this computer has, as always, problems with fonts. So our square font will denote in that slide controllability matrix. Okay, so that symbol with unknown would be that thing. Okay, somebody needs to install mathematical fonts on that computer. That's okay. Okay, so all this thing is just that curly controllability symbol. Okay. So here is my system, and I assume that d equals to 0, as I typically do. For d, just d will be equal to the previous d, but that's fine. So you have some system with ABC matrices. Again, same state space that you used to see. And this could be discrete time or not discrete time, continuous time. Any system with matrices ABC, so you have x dot equals ax plus bu, c x equals to y, and so on. Regular linear system, okay? Now we assume that the system is not controllable, okay? Which means that the rank of controllability matrix of your system is less than n. And n is order of the system's number of rows and columns in the matrix A. And we will call it R. So the assumption is that rank of that controllability matrix equals to R, which means you have R linearly independent rows or columns, okay, which is the same thing for matrices, and it is less than n. And n is the dimension of the original A matrix, which is n by n, that size. Okay, so far? So remember, rank tells you how many independent rows you have or columns you have, which is equal number. We have mathematical theorem for that rank of rows and rank of columns gives you the same number. So this number is less than n. Now you want to find such a transformation which transforms it in canonical state where you get block matrices now. Okay, the A matrix transformed will be still n by n, but it will have block which is controllable block and another block which is not controllable block. Okay, and this will be block diagonal matrix. So you'll have block of zeros, and pay attention that controllable block will be R by R because you have R independent rows in the controllability matrix. So the number of controllable poles is R. And this means that this block needs to be R by R. And this length of the numbers of zeros here also should be R to fit that dimension. Okay? So that dimension will be n minus R. Okay, the height of that block of zeros, you have multiple zeros there, depends on the dimensions of the overall matrix, okay? So the dimensions will be, this is R, total should be n. So the dimension of that zero block is n minus R, like number of rows of zeros, okay? Is it clear so far? So this is the dimension of that matrix. Similarly, this matrix is n minus R by n minus R, which is just complementing the n by n matrix in terms of dimensions, okay? And you'll have some numbers in it. It's just block of all kind of numbers. All right? And this is some other matrix of the appropriate dimensions, which will be n minus R in that direction and R by that direction. So it's R by n minus R dimensions. Okay, so the dimensions are given here. There. Okay, so far. So again, this transformed matrix will be A bar, and this will be n by n matrix, like your original matrix. And this is your similarity transforms that you want to find, the transform T. And we will find it on the next slide, okay, how you actually get to that transform. But before that, you need to understand what the meaning of that thing is. Now, similarly, matrix B transformed to that canonical state will have some vector B here of the size R, because you have R independent rows in the controllability matrix, and complementary number of zeros, which is n minus R zeros, column of zeros. Total number of elements will be again n, should be the same dimension like your original system. And matrix C will have two blocks, which are just some numbers, whatever they are. So I just call them, I call the first R numbers, I call it C1, and the second half, I call it C2. Okay, but they practically speaking the same type of numbers. It could be any numbers. It could be zeros, it could be some other numbers. All right. So in that canonical state, you'll have any kind of numbers in that matrix C. Okay, I just divide it for convenience because I will need to multiply it by something. So I'm dividing that into blocks just for convenience. And you need to remember that you can divide matrices to any kind of blocks in any order, in any direction. You are free to divide it to any blocks you find convenient. Okay, whatever works for your computations that you need to do. So for me, it's just convenient to divide it by R and n minus R elements of the vector C. Questions so far? So what I want to show you, simply speaking, is what is the physical meaning, maybe not physical, but mathematical rather meaning of having that type of system. So let's write maybe some simple example where we have all of these matrices as scalars. All right, so A will be a bar of controllable thing will be number, this will be number, this will be number. So the matrix will be 2 by 2. The system will be practically 2 by 2. Okay, second order system. Very simple. And we will write explicitly the equations, state space equations of the system to see what is going on here. Like why the system is not controllable really, what it means to be not controllable. And then we will try to expand it to more dimensions and to see what it really means to say that part of the system is not really controllable. You cannot control it. So let's say, let's pick some, if I should. That way. Okay. To record that part. All right. So let's say we have some matrix which looks like that. So A bar will be, let's say 1, 2, 0, 3. Okay. B will be equal to 1 and 0. And C will equal to something else, whatever it is. Okay. Some peculiar two numbers, whatever you want. So these are my blocks. Okay. So this is block of B controllability. Okay. This is block of B not controllability. So on. And same thing here. So this is a controllable part probably. Not remember how I selected it there. And this one is a not controllability part. Okay. Obviously, each one of these matrices is lower dimensions than the original matrix, right? Because these are just blocks that I put here. And this is a 1, 2, how I call that? Whatever. Okay, so let's see what the system is. So x dot equals a bar x plus b bar u. So this will look like that. So x1 dot will equal 1 times x1, right? Plus twice x2 plus 1 times u. That's my first equation. Okay, so it's like this one by x1, this one by x2 plus 1 times u, right? Okay, so far, this first equation. Second equation looks like that. X2 dot will be 3 times x2 plus 0 times u. That's it. This is my system. So pay attention what happens to the second equation. No matter what u you choose, because this is what controller does, it changes u somehow to modify some states. Doesn't matter what u you choose in that system. This will just decay to 0 or not 0. This will actually diverge because it's unstable. We'll choose, let's say, -3 here, then it would converge to 0, right, eventually. But you cannot control how fast it converges to 0, because it will converge like exponent of -3t. That's it. Some constant times exponent of -3t. So you cannot control that equation at all. U is not involved here. So x2 is dependent on x2, only on itself, and not on u. If this would not depend on u, but would be like plus something times x1, you still can control it through x1, right? So x1 you modify with u, and then x1 gets somehow into that equation, and then it could modify x2 somehow, okay? Then it's possible that you still can control it with u. But in that case, when variable is dependent only on itself and not on u, this is not controllable, which means no matter what you do with u, this equation will converge with the rate of exponent of -3t. So that's it, you cannot do anything about it. Now, depends if it is positive or negative, it will converge or diverge, which is converging is good for us, which is stabilizing or not stabilizing. And this is what will tell us if the system is stabilizable or not. Because if this one is +3 here, it will exponentially grow. It will be exponent of 3t times something, which is exponentially growing, positively or negatively. Right? The magnitude is growing. And you cannot do anything about it, which means your system will just blow up, no matter what you do. That design. Right? So this system would be not stabilizable if this is +3. But it is, when it is -3, like eventually it will converge. You cannot control how fast, right? In a way. But it still converges, so it's fine, right? Now, if you have more dimensions, now let's say you have bigger blocks, like big matrix A, and have multiple different elements, and you have blocks. If you have some blocks which are dependent only on themselves, let's say, I don't know, so let's say x2 dot equals 2 x2 minus 3 x3 and x3 dot equals 5 minus 5 x2. I'm just throwing random numbers, but it doesn't matter. Okay. And none of them is dependent on you. They are independent between themselves. Okay. But U is not entering any of this list of equations. Okay. So it's not connecting through any other state, through anything else. Okay. This will be not controllable part, right? So they are interconnected between them. Okay. So they kind of change each other in a way, but no input can change them, any of them. Okay. So if that subsystem, the block, and this is exactly what you will have here, okay, that part, you'll have these coefficients in that block, in that canonical form. So if this block is not controllable, you cannot do anything. So you need to find eigenvalues of the submatrix, which are coefficients of this matrix, like all these coefficients. So you need to put it on 2 by 2 matrix and to check if eigenvalues are actually converging, which are stable, right? If they are unstable, you cannot do anything with that system. It will diverge no matter what, right? This is how you think about controllability in general, right? Any questions? Okay, now we can do the same thing with the observability part. But before that, we need to find that transform. See? Clicks here to get to what we need. So how to find that transform? I'm just copying the same kind of thing. So you have all of the same matrices that you need to find. And here's how you find the transform. So the transform will have two parts, left part and right part. Each part will be columns, okay? So first of all, you have R columns, and the second part has N minus R columns, okay? Again, division into blocks, two blocks, left block and right block. So all of these columns of that part, which I will call T1, will be defined like that. And this is very interesting thing. It's kind of unusual notation here, okay? So again, all of these kind of rectangles, they are C, okay? Controllability for the matrix. You choose the first R columns of controllability matrix, your original system, okay? So you have controllability matrix, which is N by N, right? For CISO systems at least. And then you're choosing R first columns, which is B, AB, A square B, A cube B, R of them, okay? Obviously, you have not enough because you need N, not R. You need square matrix of transform, and it should be invertible. So you, first of all, choosing that thing, and then you pick any random invertible matrix here, okay? And this matrix will be R by R dimension. So you're multiplying practically N by R matrix, right? So you have R columns, which is R columns, and the length of each one of these columns is N, because like B vector, AB vector, all of them are size N. So it's N by R. Multiplying by matrix, which is R by R, which is arbitrary invertible matrix, okay? You get matrix, which is also N by R. Remember that? So if the dimensions are, you have N by R, and then you multiply it by matrix, which is R by R, you get Z by Z, which is N by R, okay? External dimensions, okay? These dimensions must match to that to be feasible, to have multiplication, and this is the answer. All right, so what happens is some magic happens here, a little bit of magic. This matrix will be inverse controllability of your transformed system, which means of that system. This will be actually controllability of that controllable part. Okay, it will be invertible, so it will be like A bar and B bar of controllability blocks. This matrix will be their controllability matrix. So you can choose it like whatever you want. So you have infinite number of possibilities here. You can choose anything you want. Typically, the easiest way is to choose I. That's the controllability matrix of the canonical system will be just I. Identity matrix. Very simple. One on the main diagonal. That's it. Okay. And then you don't even need to multiply by that R by R matrix. Okay, you're just taking first R columns of the controllability matrix. And this will be only your T1. So what happens with T2? All you need to do, you need to complement it with any vectors, absolutely any vectors of the size n, which will be independent from the previous vectors, which means you need to complement it to a basis, right? So this matrix needs to be invertible. Just pick any numbers which will make that matrix invertible. That's it, right? This is all you need. So you're picking, to find the transform, you're just picking first R columns of the controllability matrix and complementing it with linearly independent columns, whatever they are. Obviously, you have infinite number of choices here, so you can have infinite number of that type of implementations. All of them are fine. All of them will be of the same form, okay? No matter what you choose, which is interesting, unusual, I would say, to see that kind of flexibility that choose practically any matrix here, you can choose any vectors there, and you still will get the same form. But this is how it works with non-controllable systems, all right? Any questions? And we'll do some examples on that this day or maybe next time, but that's fine. Okay, so you need to remember a few things, a few comments on all of the formulas above, okay? First of all, our first rows, columns of the controllability matrix are always linearly independent, which is already kind of like, why would that be, right? It's not that obvious that specifically first R columns need to be linearly independent, but we can prove that they're linearly independent. So if you pick the first R columns, they will not be proportional to each other. All of this like B, AB, A square B, A cube B. Like if your rank is R, specifically the first R will be independent. The rest will be dependent on the previous ones, okay? Because more times you multiply by A matrix from the left, more dependent it becomes in a way, okay? I'm not proving it right now, but it's just waving my hands. You just need to remember that first R columns will be always independent in the matrix if the rank is R. Second thing, you can divide the vector as well, the same way we divided it there, right? So you have first half of the vector after the transformed, which is size R, and second half is n minus R size, dimension of the vector, right? So the first vector will be somehow controllable with U, the upper block, okay? And lower block will not be controllable with U, which means that states which are coming here, you cannot do anything with them. So they will develop by themselves somehow based on the properties of your system and eigenvalues of that non-controllable block, and you cannot do anything about that. So this part will be not controllable. Now, transfer function of that type of non-controllable system will depend only on controllable part, which means that if you're looking on that overall transfer function, G of S open loop transfer function, you remember that formula, right? C times Si minus A inverse times B plus D, standard formula for transfer functions from matrices A. It will be equal to these parts of the matrices, which are controllable parts of the matrices with bar. So you're taking these blocks, okay? This block, right? So it's like C1 bar, B controllable part, and A controllable part. This is how it works. So transfer function will actually be reduced to much smaller computation in that sense, because typically these matrices are obviously smaller dimension, right? If you have multiple non-controllable poles, your dimension will be small. So this will be very easy to compute actually. And this will be practically same thing that you're doing with cancellation of poles and zeros, right? So this cancel out. Eigenvalues of this matrix will be the values that are controllable, that you can move. Eigenvalues of this matrix, you will not be able to move. And if you remember in block triangular matrices like this one, the eigenvalues of the entire system are eigenvalues of the blocks on the main diagonal, right? So actually the original system eigenvalues will not change with similarity transform at all, but you just redistribute them in such a way that in upper block you will have all of the controllable ones, and in the lower right you will have all of the non-controllable ones. Well, the eigenvalues, you practically reshuffle them in a different way from your original matrix, right? So actually, this is a classical way to know which values are controllable and which are not. You just converted, this is like generic solution to the problem of how do you know which eigenvalues are controllable and which are not. You just convert it into that system, and then you know that all of them are controllable, all of these ones are not controllable. This is standard way. And we will learn about tricks, how to see that from the system itself without actually getting into that calculation, which kind of complicated, like you need to invert matrices, especially if system is higher order. This might be a little bit tricky how to do that, especially by hand. Like for computer order, it's not a problem. All right, any questions? So now we get to canonical non-observable form, which means not all of your eigenvalues are observable. You cannot really estimate everything. And then the question becomes like, can you design observer to that system or you can't? And again, for you, not always you even need to design observer. If you have access to all of the states, you don't need any observer. If you can measure them directly, like put sensor on each state value, right? To measure all of them directly, just connect them to controller. You don't need any observer. It will be even better and faster, right? You don't need to estimate them. But for most of the systems, you don't have access to all of the states. So you need to estimate at least some of them. And the question becomes like, can you estimate everything you need to estimate or not? Will you be able to estimate it at some point of time? Maybe you cannot control how fast you can estimate them, but maybe eventually they will converge to the real axis, to the true axis, right? To the true state. This is what you want when you're designing observers. And this is, again, dual problem to the controller problem. And pay attention that this system that you see here is very similar to what it was before, okay? And again, we're assuming that rank of the observability matrix is L, which is smaller than N, which means you have L independent rows, but not all of them are independent, right? So it's not observable system. Otherwise, it would be observable if all of them are independent, right? So L is less than N. This is what we assume for non-observable systems. Let's say you have that kind of system and you want to find transform, just that type of canonical form. Pay attention, you need to remember that we always have those dual problems where controller form versus observer form are A matrices are transpose of each other, B becomes C transpose, C becomes B transpose, that kind of thing. Same thing here, okay? Everything is dual here. You just need to switch zero block to here, which is practically transpose of the previous form, right? Here you will have some form. The dimensions will be n minus L by n minus L. So instead of R, you have L now for rank of that system, okay? And this is practically L by L observability part. So this matrix will be for all observable eigenvalues. This matrix will be for non-observable eigenvalues, okay, which you cannot change. And you really, really hope that all of them will be stable, okay? Otherwise, you will not be able to estimate the state. And if they are stable, the system is called detectable. This is detectability property, which is kind of expansion for observability property in a sense, because it says like, can you really design the observer? It's called detectable. So you can detect all of them, but you cannot control all of them, cannot converge as fast as you want to all of them in terms of state, okay? So this is the overall idea. So you divide it into observable and non-observable blocks. B could be any vector you want, any numbers, including zeros. And I'm dividing for convenience also to the same sizes of the blocks like L and n minus L blocks. But matrix C now will have block of zeros, right? And this will be that right block. So pay attention what happens here. Again, if C has particular block of zeros, this means that Y is not dependent on those x's, right? So let's see how it works. Let me get to the right board. We'll keep it as a screen. So here's how it works. Let's say you have matrix which is in that case, 0 will be here. 1, 2, 3. B will be something. C will be, let's say, 5 and 0. So the second block should be 0, right? So let's write that equation. You will have, let's take something specific. Okay. So x1 dot equals x1 plus u. x2 dot equals twice x1 plus 3 x2 plus u. Okay. You probably need to choose something which would be detectable, so we need to pick some values which will be max. Say okay. Otherwise we are in trouble. Okay. So y equals 5x1. Now look what happens. So x1 is dependent on itself and on u. So you can modify it whatever way you want, okay? x2 also will be modified through x1 and u, okay? So you can control whatever you want, okay, with particular inputs u. But what happens to y, to the outputs that you actually measure? Okay, because you want to estimate x1 and x2 from y and u. So y and u are given to you, so I'm giving you that formula, okay, I'm giving you that output, I'm giving you that input, and I want you to compute x1 and x2 in time. So what happens is it depended only on x1, but x1 depended only on itself and u. x2 is not reflected anywhere in the formula, not through x1, not through anything. Like if x1 will be some function of x2, then I can kind of compute it backwards somehow, maybe potentially. But here, you have no way of knowing why is not reflecting x2, which means you have no way of knowing how x2 is changing at all. You do not see it at all. It's somewhere inside the system is doing something, maybe converging, maybe diverging, it doesn't matter in that case. You can convert it to something convergent, that's fine, it's controllable. But in that case, you do not see it, not through any other x and not directly. So here you do not have anything with x2, and here you do not have anything with x2. But how would you know what x2 was at a particular time? There is no way. So this is what not observable system means. It means that particular states are not reflected in any way in the output. And the only way you can actually compute them back is from the output. This is your only thing that you have in observer design, right? So in that case, you can't. Okay. Now, some of the states, like if the system is in that canonical state and this eigenvalue is kind of diverging by itself, you know that it will go to 0, right? Eventually, the error will go to 0 eventually, if it is stable. So you don't know when, but eventually the x will converge to the real x somehow, but you don't know when. But if it is unstable, well, and not observable pole, the error will diverge, because if you remember, the error is an A minus LC matrix, okay, in observer. Okay, this is how error diverges, right? So that matrix will be unstable, and if this matrix is unstable, the error will be going exponentially up or down. So they will never converge to each other. So you will never estimate the correct X. And you will never be able to control that as well, because your estimated X will be wrong one. And getting more and more wrong each time, right? This is the idea of absence of observability. Any questions on that before we get to how to compute the transform, which is, again, very similar to previous one, but you'll get through that. So here's how you do that. Instead of controllability matrix, now use observability matrix. You take in the first L rows of the observability matrix, which are practically C, CA, CA squared, and so on. L of them, which is rank of the system, original system. Then you multiply on the left by L invertible matrix of any kind, like pick your matrix. All right, you can pick any L by L invertible matrix, multiplying by that kind of other matrix. Now, again, similarly to previous time, this will be your inverse observability matrix of the observable block. And you can pick it to be I or any other matrix, whatever you prefer. I is just easier, you don't need to multiply anything. When you choose it I, then this will be just list of vectors like that, row vectors from the matrix of observability. And then you need to complement it with n minus L independent rows. So you just pick any rows which are linearly independent and will make that matrix invertible. All right? Practically, that's it. This is how you find that transform. Okay, just based on that formula. Questions? That's very similar. Before you took like all of the columns of the controllability matrix, complemented that with independent rows to get it n by n. And here you're taking rows of the observability matrix and then complementing it to get n by n matrix. That's it. Okay. So just to recap on everything. It's impossible to move non-controllable eigenvalues if they are not controllable. So you can design controller only to move poles which are controllable. So if they're stable, great. You still can control the system. They will converge somehow. If they're unstable, you might be in trouble. You probably need to design another system. Similarly with estimation, if the poles are stable of non-controllable parts, that's okay. You eventually will be able to estimate the X that will at least converge at some point of time to the real state. But if it is not, unfortunately, you cannot design observer. So you cannot do anything about it, unfortunately. So try to design your system always in a way that it will be both observable and controllable. But if you cannot, at least the poles which are not controllable or not observable are stable. Okay, then you still can do everything you need to do with your system. Okay. So here's the terminology that I already mentioned. We just officially define it. The system is called stabilizable if all its non-controllable eigenvalues are stable. This practically means that you can stabilize the system. All right, this is the thing. So you can design controller for the system. And the system is called detectable if all of its non-observable poles and eigenvalues are stable, which practically means that you can design observer to that system. And to stabilize the system, obviously, for where you need both of them, state feedback and observer in the closed loop, it needs to be stabilizable and detectable. But this is pretty obvious because You cannot design half of the system, obviously, you cannot design the entire system. This is how it works. Any questions? Detectability and stabilizability. Again, this is just extension of the controllability and observability properties, but very important extension, where it actually tells us if we can do something or we can't. So a few tips and tricks, I guess. In most of the exercises that you will see, at least, typically you can use some of these rules to avoid computing the inverse matrices and all these complicated things, especially if you see like matrix 4x4. I'm definitely, like in homework, let's say you see matrix 4x4, I'm not asking you to inverse, to find transforms 4x4 or matrices 4x4, which are invertible, and then to invert that matrix. Probably I'm looking for some sort of tricks that you need to learn, okay? So pay attention to tricks. And I think that these tricks are even more important than that entire theory. And this is why. Not because like this is for homeworks or any other purpose of like busy work, right? Instead of like using computer for inverting 4x4 matrices, okay? You can do that. This is not a big deal. Using these tricks gives you intuition about the system when you are looking at the system. So you need to look at the matrix A that you have, matrix P that you have, matrix C that you have, and to get already some sort of intuition how it works, okay? So some sort of feeling about like, will that do whatever you think it will be doing, in a sense. And that experience comes only from understanding that type of tricks. Then you just looking at the system, spend some time just observing it, okay? Just looking at like how it looks like. Sometimes you have all kind of blocks of zeros. Sometimes you have all kind of zeros in different places, you know? And then you can do that type of logic that we did on the board there, okay? Just to understand, oh, this X is dependent only on itself and not on you. And then I cannot control it really. But you can do that by observation. You don't need really to compute it into that form, canonical form. Sometimes you have that as part of your system. Or you have all kind of topological observations that you can do. Like you know how many non-controllable or non-observable poles you have, but your system is limited order, so you can actually know that some of the poles must be both non-controllable and non-observable, okay? Or it could be unstable. Let's say, simple example, you are looking for, like, if your system is non-detectable or not stabilizable, okay? But you know that all of your eigenvalues are not stable, and you have some cancellation, whatever it is. So you definitely know that your system is not controllable, not detectable, or not stabilizable, okay? Right? Because all of them are non-stable. You don't need to compute it really. You don't need to do any computation. It's just pure logic. Because you're saying that at least some of them need to be not detectable and all of them are unstable. So it's not detectable, right? If all of them are unstable, no matter what. Because each one of them could be that one which is not detectable, and you don't care which one, really. You care that it's not detectable. You don't care which eigenvalue is not detectable. So you don't need all of these transforms and all of the other stuff. So many of the problems in controls you can solve without actually computing it. You can do that using intuition and understanding of how stuff works. And these are a few things that you need to pay attention to, okay? So we have discussed already all of this, like observable, non-observable blocks of the matrices. This will be controllable and not controllable matrices. These are the definitions that we had in the previous slides, okay? And here are the things that we can do to identify which of the poles are controllable, not controllable, observable, not observable. The standard way is to compute the transforms. It works always. There's a standard way. You always can find the transform using columns of the controllability matrix, of rows of observability matrix, complementing to the basis, computing similarity transform, long process, 500 computations, you're done. You have all those blocks, block of zero, you know, which is controllable, not controllable, done. Okay, finding eigenvalues of these blocks. That's it. Practically, this is how you do that in standard way. But let's say you do not want to do that and you have other ways to do that. Number one, you can diagonalize the matrix. You can find diagonal representation of your system, okay? If you remember, diagonalization, you also find in some transform, but sometimes it's easier than doing that type of transforms. And sometimes you have it almost diagonal form. Unfortunately, not all matrices could be diagonalized. Sometimes if you have like double eigenvalue at the same point, sometimes you can, sometimes you can't. If you have different eigenvalues, then you always can. But if you have like double or triple eigenvalue at the same point, sometimes you can, sometimes you can't. Okay, then you have Jordan forms and other things which are near diagonal, but not exactly diagonal forms. Okay, we will not get into details of that, but let's say you have diagonal forms. You have matrix A bar, which is diagonal, right? All of the same eigenvalues sitting on the main diagonal, but not in order like you have in canonical form, where it's like divided into like controllable, not controllable. Okay, now they are in random order pretty much. All of these eigenvalues on the main diagonal. So some of them are positive, some of them are negative, some of them like stable, not stable, whatever. Okay, but you have diagonal matrix A bar. You have matrix B, which is whatever that matrix is, diagonalization matrix inverse times B of your original matrix. Matrix C is C times the diagonalization matrix, and D is the same D as your original matrix D. Okay, so each zero in vector B bar, which is that computed vector, will tell you which eigenvalue corresponding to the same line is not controllable. Okay, and pay attention, this will give you practically the equation x particular index dot equals something times the same vector, the same, not vector, the same state, the same x, okay, with the same index, and no u. Right? This is what that thing means. Like the number one phrase that you have here, it says that you have some equation which looks x particular dot equals something times that same x. And that's it, and no u. So you cannot control it, and it's not dependent on any other x. Right? It's like x3 dot equals minus 5x3. This is your equation, one of your equations. This is what it means. And this is exactly the type of non-controllable states that we've seen on the board there. Right? This is exactly what it is. You have state which is dependent only on itself and not on input u. So you cannot control it. So if this eigenvalue is sitting on the main diagonal of the matrix A, right? This will multiplied by. That's how it works. Similarly, if you have 0 in matrix C bar, which is a transformed matrix C, this is like C times T. If you have 0 there, this means exactly the same thing that we've seen on the board there, which means Y is not including any information on that particular state, on that particular X, right? So this X is multiplied by 0 in that matrix C, which means C times X will be 0 times that particular X, and it will not be reflected in Y. And also, in the same kind of thing, you will have column where this X is dependent, like other X's are not dependent on that X, right? So if they are not dependent on that X, you cannot see it from anywhere, not from other X's and not directly in the output. It's not reflected anywhere. That's exactly what it means. So zeros in B matrix mean you have non-controllable eigenvalue, and you know which one is that because it's sitting on the main diagonal on the same row. Same thing, 0 in C matrix, sitting on the main diagonal, that eigenvalue is not observable. Okay, whatever corresponds to your matrix. Okay, questions on that? All right, other way to do that. If you compute a determinant of Si minus A plus Bk, and you're doing that for particular eigenvalue of your system, so you pick, like you can compute all the eigenvalues of your given system, okay? And you want to identify if it is controllable or not controllable. So compute that thing. And you will be doing that anyways for computing the controller, right? This is exactly the thing that we are doing for controllers for a generic S. It's exactly the same thing. So you can compute determinant, it will be polynomial in S, right? Remember that? This is exactly how you compute the controller. You're computing that equation equals to desired equation in closed loop. This closed loop polynomial. So what I'm saying, that if this thing will be equal to 0 for all k, which means it will not even depend on k, then S, that particular S is not controllable. In other words, the polynomial will have factor of S minus Si, which is factored out in the polynomial multiplied by something as a function of k. So for that Si, it will be S minus Si, it will be 0 times whatever is a function of k. And we don't care what that is, okay? This is exactly what it means not to be controllable. Just cancels out. You cannot control it. Same thing with observability matrix. If you remember, this was the determinant that we used to find the observer, okay? So we compare that to desired polynomial of observer. So LC is replacing BK in that sense, right? Same thing. If this determinant is 0 for all L, or any vector L, so it's not dependent on L, practically speaking, then obviously this specific Si is not observable because it's not reflected as a formula at all. It's not a function of L. You cannot control it with L in any way. Okay? L is not affecting it in any way, right? So again, the polynomial that you will get here is S minus Si times something, whatever it is. So it will be factored out in that polynomial. Then it's not observable. If one of the states look like that, so x dot equals something times the same x for any constant alpha. It depends only on itself, so it's not controllable. You cannot do anything about it. You can use also combinatorial considerations. This is probably the most difficult one to get experience with, because here you need to think a lot about like logic of like what could be or could not be, and all the possible combinations of poles. Would they be stable, unstable? So here's one specific example, okay? Let's say the system is order 3, which means it's like 3 by 3 matrix A, okay? Whatever that matrix is. Rank of controllability matrix is 1, and rank of observability matrix is 1. Very easy to compute. You compute those two matrices, computing rank, you have only like one independent column or row in both of these matrices. This means that you have 2 non-observable ones and 2 non-controllable ones, right? Because this is complementary to the rank. So rank tells you how many controllables you have and how many observables you have, which means you have, if rank is 1, then you have 2 non-observables and 2 non-controllables, right? This is combinatorial considerations, right? All right, so let's say 2 of your eigenvalues also unstable, right? If you assume something like that, you know for sure that the system is not detectable or not stabilizable, okay? But you know even more than that, it's for sure non-detectable and non-stabilizable. Why is that? You cannot stabilize it and you cannot build observer to the system at all. And I even not telling you what the system is, right? But I know that just from combinatorics. Because to make it at least detectable or stabilizable, you need 2 poles which would be stable. And you have 2 of them unstable out of 3. Like, can you pick 2 stable out of 3 when 2 of them are unstable? No matter what pair you choose, you always have to choose at least one which is unstable. Like if you have, for example, eigenvalues which are, I don't know, 1, 2 and -3. Okay, so one is stable, two are unstable. Like, can you pick two stable? You can't. Like, no matter which pair you choose, you always will have at least one unstable. And you know that you have two non-controllable, which means that you want them to be stable somehow, okay? Like pick. You can't. Same thing with detectability. You want two observable ones stable, non-observable ones stable, right? Cannot pick 2 out of 3 because you don't have enough stable ones. So just regardless of what the system was, if I know that information, which is very easy to compute, these are just eigenvalues of your open loop system, right? And you can compute rank of the controllability, rank of the observability. These are the 3 numbers that I need to tell you that you cannot stabilize the system and you cannot design observer for the system. Done. You don't need to compute anything else. Okay, so you have many questions and intuitions which are coming from different kind of considerations. And I understand this is difficult now. Okay, I'm not assuming that you will kind of catch it and now run with it. That's fine. I'm just saying you need to have all kind of logical thinking about things which might be important for understanding how system behaves. Okay, based on how many observable, not observable poles you have, about like where your eigenvalues are, things of that kind. You just look at them, observe them. If you can get to some conclusion from that, great. You saved your time. If not, you can go the standard way and compute all these transforms and other things. That's fine. Okay, until you get that intuition, right? Any questions? Okay, so a few interesting questions now. What can you tell? Have you ever seen transfer function which is 0? This is very interesting transfer function. So next time, what I want to show you some exercise that you can have state space representation of a particular system where none of the vectors A, B, or C are zeros, but the transfer function is. So you can have that magical system, and you have like infinite number of that type of systems, actually, where your transfer function is 0, which means it multiplies everything, every single frequency by 0. Like the output is always 0, but none of the matrices is 0. That is very interesting exercise in itself. But what can you even say about controllability and observability of eigenvalues of that type of system, which has 0 practically? Because even like if you cancel all of the zeros and poles, you would get practically 1 or constant, right? If all of them cancel, you will not get 0. But I'm talking about system which is 0, completely 0. So can it be controllable and observable? Just yes.
It is observable, but it is not controllable.
So it's definitely not minimal simple system, okay? So it could be observable and not controllable, okay? But maybe not. It could be all kind of things, which is interesting. We will see that next time. I will show you some exercises how actually to find all these transforms and other things, and we will solve kind of theoretical question related to transfer function 0, which are kind of weird and interesting. So what can you tell about system stabilizability and detectability, where all of its eigenvalues are on the left in continuous time system? Can you say something about the detectability and stabilizability?
All the eigenvalues to the left. So when would it be controllable and
They're not controllable. Some of them might not be controllable. Depends on the system.
it's
Okay, let's start with stabilizability. what can we say about stabilizability of the system, which has all of its eigenvalues to the left, and it could be any kind of system. It's stabilizable. It's stabilizable because even if some of them are not controllable, they are still stable. This is how stabilizability is defined, that all of the non-controllable ones are stable, and we don't really care what happens to controllable ones. Okay, they could be stable or unstable, it still will be stabilizable. Okay, but if all of them stable, obviously it's stabilizable. Same thing with detectability. Like detectable means that all of the non-observable poles are stable, but you don't really care what happens to observable poles, right? They can be stable or not stable, but I'm saying they are stable. So it's even better, okay? You don't need to move them much. You can keep them where they are, maybe. So the idea is that systems which are stable in open loop, regardless if you have cancellation or you do not have cancellation, they are detectable and stabilizable always for all stable open loop systems. The problem is only when the system is unstable in closed loop and you have cancellation of unstable pole. This is where the problem comes. And you can always technically choose them if you want it to be controllable or observable, because you can really choose that. If you have cancellation, for example, of unstable pole, you obviously want that to be controllable, which means that you will have to actually measure all of your states. You will not be able to design observer for that system. And this will mean that you will need to pay a lot of money for your sensors and to put sensor on every single state to actually measure it instead of estimate it from the output, because you cannot. It's not reflected in the output. But you will be able to stabilize the system still, okay, because of your implementation of the system. So it's doable. It's not that bad, okay, if you cancel in some unstable pools. It's just more expensive. Any questions? All right, thank you.